Good evening, sir. Today in this explanation I am going to explain about skew symmetric matrices. Myself B. Saichand and my roll call is 21951A1269 and I am from IT department B section and the subject is mathematics. So definition of matrix. Matrix in mathematics is defined as an array of numbers arranged in rectangular fashion and divided between rows and columns. It contains all the numbers arranged in square brackets. The operation of matrix is a very important topic in the mathematics for the board exams as well as for the engineering entrance exams. So definition of skew symmetric matrix. A skew symmetric matrix is a square matrix that is equal to the negative of its transpose matrix. It is important to know the method to find the transpose of a matrix in order to understand a new symmetric matrix better. Here we have considered a matrix. The basic formula representing a skew symmetric matrix is B is equal to B transpose or else A is equal to A transpose. So a square matrix B which of size n into n is considered to be a skew symmetric matrix if and only if B transpose equal to minus B. That is, the transpose of a skew symmetric or antisymmetric matrix that is equal to the negative of the matrix. This can be represented as if B is equal to Bij m into n into Bij into m is the skew symmetric matrix. Then this is the example. Here n is natural number. If we put I is equal to j for all I, this means that all elements that are present diagonally in a skew symmetric matrix are 0. Then properties of skew symmetric matrix. The two important conditions for a matrix to be skew symmetric are that it should be a square matrix, that is the number of rows and columns should be equal, and secondly that the given matrix should be equal to the negative of its transpose. Here are some of the important properties of a skew symmetric matrix. When two skew symmetric matrices are added, then the resultant matrix will always be a skew symmetric matrix. Considered two skew symmetric matrices A and B such that A transpose is equal to minus A and B transpose is equal to minus B. Then we have A plus B whole transpose is equal to minus of A plus B. The trace of a skew symmetric matrix equals 0. That is, the sum of all the elements in the main diagonal is equal to 0. The real eigenvalue of a real skew symmetric matrix A is lambda equal to 0. That means the non-zero eigenvalues of a skew symmetric matrix are non-real. Addition and difference of two symmetric matrices result in symmetric matrix. If A and B are two symmetric matrices and they follow the commutative property, that is B into A is equal to B, A into B is equal to B into A, then the product of A and B is symmetric. If matrix A is symmetric, then A power n is also symmetric. Then n is an integer. If A is a symmetric matrix, then A inverse is also symmetric. Theorems related to skew symmetric matrices. There are two important theorems related to skew symmetric matrices in this session. Let's learn about these theorems along with their proofs. So theorem 1. For any square matrix A with real number elements, A plus A transpose is a symmetric matrix and A minus A transpose is skew symmetric matrix. So here's the proof. Let P is equal to A plus B, A plus A transpose. Transpose of P can be given as P transpose is equal to A plus A transpose whole transpose equal to A transpose plus A transpose whole transpose, which is equal to A transpose plus A and which is equal to P. So then A plus A transpose is a symmetric matrix. So let's assume Q is equal to A minus A transpose. q power t is equal to a plus minus a transpose whole transpose, which is equal to a transpose plus minus of a transpose whole transpose, which is equal to minus of a minus a transpose, which is equal to minus q. So a minus a transpose is skew symmetric matrix. So theorem 2 is any square matrix A can be expressed as the sum of the symmetric matrix S and skew symmetric matrix. Thus any square matrix can be expressed as the sum of the skew symmetric matrix and a symmetric matrix. So determinant of skew symmetric matrix. If A is a skew symmetric matrix which is also a square matrix, then the determinant of A should satisfy the below condition. Det of A transpose is equal to det of minus A, which is equal to minus 1 to the power of n det A. The inverse of a skew symmetric matrix does not exist because the determinant of it having odd order is 0 and hence it is singular. Eigenvalues of skew symmetric matrix. The eigenvalues of a skew symmetric matrix are either 0 or imaginary values. The real eigenvalues of a real skew symmetric matrix A, lambda equals 0. That means the non-zero eigenvalues of a skew symmetric matrix are non-real. Proof. Let A be a square matrix and lambda be an eigenvalue of A and X be an eigenvector corresponding to the eigen lambda value lambda. So this is the proof. If A is a real skew symmetric matrix, then its eigenvalue will be equal to 0. Alternatively, we can say non-zero eigenvalues of A are non-real. Every square matrix can be expressed in the form of sum of a symmetric and skew symmetric matrix uniquely. So trace of a skew symmetric matrix. The trace of a matrix is defined as the sum of all its diagonal elements, as discussed under the properties of a skew symmetric matrix. The diagonal elements of a skew symmetric matrix are 0. Therefore, the trace of a skew symmetric matrix always equals 0. Important notes on skew symmetric matrix. Here is a list of a few important points that should be remembered while studying skew symmetric matrix. A matrix for which the transpose form is equal to the negative of the original matrix is called a skew symmetric matrix. Any matrix can be expressed as a sum of symmetric and skew symmetric matrix. For a square matrix A is equal to 1 by 2 of A plus A transpose plus 1 half of A minus A transpose. If the order of a skew symmetric matrix is odd, then its determinant is equal to 0. So let's recap what we studied in this presentation. First of all, definition of a matrix. Matrix is a mathematics is defined as an array of numbers arranged in the rectangular fashion and divided between rows and columns. It contains all the numbers arranged in square brackets. The operation of matrices is very important topic in mathematics for the board exams as well as for the engineering entrance exams. So here comes definition of the skew symmetric matrix. Skew symmetric matrix is a square matrix that is equal to the negative of its transpose matrix. It is important to know the method of find to transpose of a matrix in order to understand a skew symmetric matrix better. Here we consider a matrix A. The basic formula representing the skew symmetric matrix is A is equal to minus A transpose, or B is equal to minus B transpose. So a square matrix B which of size n into n is considered to be a skew symmetric matrix if and only if only B transpose is equal to minus B. That means the transpose from form of skew symmetric matrix or antisymmetric matrix that is equal to the negative of the matrix. This can represented as follows. So here are properties of the skew symmetric matrix. The two important conditions for a matrix to be a skew symmetric matrix are it should be a square matrix, that is the number of rows and columns should be equal to same, and secondly the given matrix should be equal to the negative of its transpose. Here are some of the important properties of a skew symmetric matrix. When two skew symmetric matrices are added, then the resultant matrix will always be a skew symmetric matrix. Consider two skew symmetric matrices, matrix A and matrix B, such that A transpose is equal to minus A and B transpose is equal to minus B. Then we have A plus B whole transpose is equal to minus of A plus B. So the trace of a skew symmetric matrix equals 0. That is, the sum of the elements in the main diagonal is also equal to 0. The real eigenvalue of a real skew symmetric matrix A, lambda equals 0. That means the non-eigenvalues of a skew symmetric matrix are non-real. So these are some theorems related to skew symmetric matrix and determinant of a skew symmetric matrix. If A is a skew symmetric matrix which is also a square matrix, then the determinant of A should satisfy the below condition, which is det of A transpose is equal to det of minus A, which is equal to minus 1 power n det of A. The inverse of a skew symmetric matrix does not exist because the determinant of it having odd order is 0 and hence it is singular. So eigenvalues for skew symmetric matrix, then trace of a matrix, symmetric matrix. Then this is important notes on a skew symmetric matrix. So a matrix for which the transpose form is equal to the negative of the original matrix is called a skew symmetric matrix. Any matrix can be expressed as the sum of the symmetric and skew symmetric matrix. For a square matrix A is equal to half of A plus B whole transpose plus half of A minus B whole transpose. If the order of a skew symmetric matrix is odd, then its determinant is equal to 0. So that's all in this presentation. Hope this presentation was informative. Thank you.